So as Kate asked me to talk about the efforts that we have been doing about sonification in astronomy, I decided to start from this 2022 review that we put together. And then I will just conclude mentioning some of the most recent efforts that we have been carrying out to evaluate the effectiveness of sonification in different directions, let's say, for research purposes, educational purposes, and public engagement and outreach purposes. So I would say that astronomy is the stereotypical visual science. We are all used to think of astronomers. I am an astronomer, but I would say we are all as a community used to think that astronomy, we do it with the eyes. Not only now the astronomers look into the telescope. This is something we don't do anymore, but still remains in the general culture as an image and the imagination of the astronomer work. But more modernly and more in general, I would say telescopes collect light, researchers do research using visual tools, and astronomy is presented to the public and in the schools by using beautiful images and visualizations and videos. However, this has mainly two big limitations. The first one is that we limit the study of astronomy and science in general to a monosensory exploration, whereas we are used to explore reality with all our senses. So it's a multisensory exploration, actually. But also we lack tools that allow blind and visually impaired people to access astronomy research, outreach, and education. And I would say that there's really no reason for that, because I would say we are all blind to the universe. By eye, we can see about 1,000 stars, the brightest and the closest, but then we need telescopes, so instruments to see beyond that. And also the light that we can see with our eyes is just a tiny fraction of the electromagnetic spectrum. All the rest of the radiation is not perceivable with our eyes. And again, we need instrumentation. And what the instrumentation does is to provide us with numbers that we translate into images to make sense of them. So recently, we have been taking up the challenge of translating these numbers into sound. And I would say that there is a huge potential for these multisensory approaches to astronomy education, research, and that this really benefits everyone, sighted people and visually impaired people at the same time and in the same way. So I'm not saying that we need to replace all the visual information in astronomy with sound, but we should enhance visuals with sound, and this also will make astronomy accessible. So starting this, the starting point, let's say, of this effort was to try and gather what has been done so far in astronomy about sonification. So a great starting point, and I would say great help in that research was the Data Sonification Archive. Here there is a typo in the title, but okay, the Data Sonification Archive, Sara Lenzi is one of the responsible for it, and she's on this call, so I'm sure if you have questions, she will be not only able, but probably happy to answer them. The Data Sonification Archive is a great repository where sonification in different fields are gathered, and among them, astronomy is one of the fields and maybe one of the most populated fields. So we use this instrument to gather the astronomy sonification projects that were available until 2022, the year of the study. So we discovered in this way that the first sonification study in astronomy dated back in 1960. And at that time, this project was meant to reveal some signatures, some features in data. So the purpose was research. Since then, many new projects started to grow and to appear. And since 2016, between 8 and 19 new projects started to appear every year. So we gathered them with the idea to consolidate what had been done, to share knowledge, and to start working towards some shared standards to evaluate the effectiveness of sonification. So what we did was to try and understand what was the main goal of those 98 projects. And most of them, so 35% of them, had public engagement as the first goal. A good number of them, so 25%, were created for research purposes. 17% had art in mind, so they started from an artistic, let's say, need, and they were mainly created by artists. Only 13% of them had accessibility in mind. So this is less than we expected. However, many of these projects had accessibility as a secondary goal. So accessibility was not the first goal in the first place, but anyway, including sonification, we are making astronomy accessible, irrespective of the goal that we have. And most of the users that are intended of these sonifications are the general public. So this is almost 80%. And researchers are the remaining 20%. We also did a bit of study of what were the multimedia. So very often sonification was made through a GUI or interfaces. In many cases, it was accompanying visual elements. In some cases, only sonification was created. So yeah, we gathered all these projects. We also tried to divide them into their main purpose, so research, education, and public engagement, and to give some examples in this review that we put together and find some patterns. However, at that time, we also tried to identify what were the main challenges and the main open points. What we understood was that standards were lacking and proper evaluations were lacking. So many astronomers that were enthusiastic about sonification were creating these projects, but they were not really evaluating them. So we started to do so. We started to pair up with sound designers to have better sounds and with psychologists to do proper evaluations. And so in the following, I'm showing you some projects that we have been pushing in recent years to evaluate sonifications in these different branches, let's say. So the first case is an evaluation of sonification for research purposes. I would say the astronomical content is not really important, but the idea is that we were trying to sonify light curves. So we have a star and the planet that passes in front of the star. As in the case of an eclipse, when a planet is in front of the star, there is a dip in the luminosity of the star. So usually astronomers recognize this dip as a decrease in luminosity in a graphic form. So we tried to map the brightness of the star with pitch and with the duration of the sound, and to evaluate what was the success rate of the users in the two cases. So I will let you listen to one example. So the first one is a mapping of brightness to pitch. The dip in the star brightness is perceivable as an increase in pitch. Okay, I hope the sound came through. Yeah, okay. Now the second example with the duration of the sound. Longer sounds indicate the transit, so the passage of the planet in front of the star is happening. Okay, we also had a combined stimulus of pitch plus duration, which is a combination of these two. So this one that I let you listen to was let's say, an easy example, but we had cases where the noise was much more important, and therefore it was more difficult to find the signal. We repeated the experiment with astronomers and non-astronomers. We asked them to find the transit, so this signal, in visual data and in sonification using the different mappings. What we concluded is that the performance is much better in general with visualizations rather than with sonification, but the results with sonification are above chance level. So they're good. What I found interesting is that astronomers were performing much better than non-astronomers with visualizations. And the reason for that is that we, as astronomers, are used to look at noisy data and at graphs. We are trained to look at graphs. We do that every day. So what we start to think is that if we have training since the youngest stages to listen attentively to data, probably the performances with sonification will also improve. And so I would say this is opening now the way and the path to do some more experiments that, based on the training, what kind of training we need, how long does it have to be, and so on and so forth. The other point that I found interesting in that experiment was the calculation of the response bias. So how much the astronomers or non-astronomers were prone to say, yes, there is signal, or no, there is no signal. What we found is that especially in the low signal to noise case, so when it's difficult to find the signal, with graphs, usually people would say, no, there is no signal, even if the signal is there. Whereas with sonification, there is less bias. So the conclusion here is that with graphs, we might be missing some detections just because we are very conservative. And of course, for scientists, this is a problem. So I would prefer to have more false positives than missing detections or missing events. So in this case, sonifications might be useful to avoid missing detections. So this is just an example about the use of sonification for research purposes. Another experiment we have been carrying out is the use of sonification for education. So in this case, we did an experiment with the middle school kids. There are 150 kids. They're mixed classes in Italy. With sighted and blind kids. We were using Educoi, which is a tool. So you have to move the hand in front of the computer, and a camera recognizes the position of your finger and lets you listen to the sound of the color of each pixel, depending on where your finger is touching. We used, in this case, a mapping that is, let's say, natural mapping. So we associated the blue color with bubbles, so water bubbles, the red color with the sound of fire in a fireplace, and the green color with the chirping of the birds and the sound of leaves reminding of a forest. The study was trying to evaluate how effective this sonification was in color recognition and shape recognition. We first used some sketches and some geometric shapes, and then the shapes of galaxies. So I will first let you listen to some of these sounds so you can maybe better imagine the experiment. In this case, there is a hand that is going on top of the image of a galaxy that has different colors, red, blue, and I will let you listen to some sounds. Okay, this was with the musical instruments. You can also change the mapping and use the natural one that I described. The two different sounds that you could hear were blue regions or red regions in the same galaxy. So what we concluded from this study is that color recognition was extremely easy for the kids. We explained it once, and they were able to have, let's say, success rates that were about 100% immediately. And also the students remembered the colors after we repeated the experiment after a few months, and they could remember the association between sound and colors after a few months without using the tool. So color recognition was easy for them, especially for the sketches where only one color at the time was presented. When we presented them with real images of galaxies where different colors were overlapped, they could still recognize multiple colors happening at the same time. So they could listen, in this case, to the blue and red color, bubbles and fire at the same time. Success rate in color recognition was about 80%, so still very good. Recognizing shapes was more difficult. Again, it was above chance level, but it was about 60%. So there is more work that needs to be done on this. Finally, one last example about public engagement. Together with Chris Harrison, we took up the challenge of designing and creating a planetarium show starting from sonification instead of visuals. So planetarium shows are usually made of amazing videos. We took up the challenge of reverting, let's say, the order and start from sounds. So in this case, the planetarium show is a journey through the solar system. And there is a spacecraft that goes around, but it starts from Chile, where one of the main observatories on Earth is located. And one of the first scenes is the appearance of stars in the dark sky in the desert. So now I will let you listen to the clip. Stars of different colors have different sounds, and the spatial direction of the sound represents the location of where the star appears in the night sky. So really, we're translating data into sound in an accurate way. Okay, also in this case, we used the questionnaire to gather the experience of the participants. We had adults, children, visually impaired and sighted participants. In this case, we were asking mainly two questions. The first one was, after the show, how much do you think that studying or working in astronomy is accessible for blind or visually impaired people? And most of the people, both adults, children, they said more. I believe now that astronomy is accessible. The other question was, after the show, how much do you think that studying or working in astronomy is accessible for blind and visually impaired people? And also in this case, for sighted and non-sighted audiences, the answer was more. I'm now more sure. So I would say that using sonification for public engagement enhances the perception of astronomy as an accessible science for everyone. And so this is, it allows us to change the perspective of the public at least a bit. So I think I would now stop. And if anything was unclear or if you have questions, I would be happy to answer.
Well, thank you, Anita. One of the questions I was thinking about right away was just your summary slide. If you could do us the favor of explaining this graph and how to interpret it, because I know that was a challenge. But I really enjoyed all the new information that you had up and the new studies that you guys have done. That's some really great work in the last couple of years. Appreciated hearing about that.
Yes, what I'm showing in this slide is a very complex graph with lots of, let's say, visual information. So there is a bar on the left-hand side. There are some words written: public engagement, research, art, accessibility, and education, and the percentage next to each one. This indicates how many projects have, for example, public engagement as the main goal. Each of these categories have different color. And there are curves that connect these categories to a second bar that is called user. This is general public or researchers. So what this first part of the graph is telling us is what are the users of the projects that have public engagement as main goal or that have research as main goal. So for example, all the public engagement works have the general public as a user. The research works instead have, in a minority of cases, the general public as the main user, and in the majority of cases, the researchers as the users, and so on and so forth. And the second part of the graph connects the users with the, let's say, multimedia. And the idea is the same, to try and understand how the different sonifications are, let's say, rendered in the multimedia way. Was it clear enough, Kate?
Yes, I appreciate that. And I'm going to take on a challenge of seeing if I can create a tactile version of that, because I don't think a sonification of that will work well. So I think that that information that's there is of high interest in understanding that when you're starting on the far left, that there can be a split in your actual user audience and what it's going to be used for. So to follow those is your challenge here. So thank you. Other questions, just go ahead and unmute and ask, because we don't have a very large group here. So if you'd like to have Anita go back and answer any questions about any part of the presentation, please do.
This is Amy Bauer. I have a question. Well, comment first. That was very interesting. It's really cool stuff that you've been working on. My question goes back to the planet transit example, and you tested it with scientists and or astronomers and non-astronomers. Were any of those subjects blind or low vision?
No, we had a few, but not enough to really draw conclusions. So we mainly focused on astronomers and non-astronomers because we had a good statistics of both groups. But no, the other reason is that we also compared to visuals. So clearly didn't really make sense with a big pool of visually impaired people.
Right. But and I agree with your conclusion that scientists have more experience and are trained in the interpretation of visualizations. But similarly, blind and low vision people, although I don't think many receive training in interpreting data sonifications, they may be nonetheless more in tune or more sensitive, more aware, more cognitively engaged with audio. And so, they may be able to interpret. I just think it would be interesting using the audio only to compare blind and low vision population with the sighted population.
Yes, thanks. I agree. What we are doing right now, first a comment. Yes, for training, I also mean not only the training we get, let's say in schools, but also the daily training of just repeating the same action over and over. That is what researchers do. We keep staring at graphs and we get used to it. So trying to understand if that's really the difference between experts and non-experts, we are now repeating a similar experiment with musicians and non-musicians to try and understand if training in listening makes a difference. Yes, the next option is also to try blind and non-blind people. That's also possible.
With audio only. Yeah.
With audio only, of course.
Yeah. Thanks.
Yeah.
I have to chime in here and point out that my friend and colleague, Matt Henry, before he came to work with the Everett Group, worked at the Air Force, the U.S. Air Force, which is where I first met him. He was the conductor and commander of the U.S. Air Force Europe Band. And he is a top-notch musician. So if he was getting fidgety when you were showing, Anita, showing the sonifications of the galaxy, he texted me directly and said, "Oh, that should be a trumpet," which is what Matt plays at the center of the galaxy. I told him no, it needed to be some very low instrument like a bassoon, because there's a big black hole in the middle there. So just be aware there's going to be complications when musicians get involved, okay? Sorry.
Yes.
That's very good. Other
I had a-
questions? Go ahead, Adrian.
Yeah. Hi, Anita. I had a quick question. I was curious about the experiment you were doing with the middle school students, and were you tying that into any particular scientific curriculum? Was it about why stars would have different luminosities, or were you connecting it with the electromagnetic spectrum, or how do you think that could be tied into the science curriculum?
We were linking it with the science curriculum, and then interestingly, the art teacher got very, very interested. So I think they then started to use the tool within art classes, but that was not our main goal. So we didn't really follow up with that. As part of the science curriculum, I mean, the first part was all about geometric shapes. So geometry is an easy link. And then in science, students in Italy start to learn also something about space, planets mainly. But the teacher allowed us to talk about galaxies. It didn't really, it was not really a problem for them. So the connection was geometry for the first part, and then science, a bit of astronomy for the second part.
And when you do a study like that, I'm imagining you're working with a very small sample. Do you at some point then want to scale that up and have, hundreds or thousands of students be testing that sort of a technique with the hand and the colors and shapes?
It was not really a small sample. We had 150 students.
Oh, okay.
Yeah. Now classes in Italy have they call it a computer room, where there are about 20 computers. That means one per kid. So of course we were making the screens blind, so the students were moving their hands, but they couldn't see the images. They could just listen to them. At that point, sighted and non-sighted students had the same opportunities, let's say. But each student at that point had one computer, and they could run the experiment all simultaneously. So that was really a science class that lasted about 1 hour, and we were gathering and collecting data while, let's say, teaching. But yeah.
Okay, I guess I assumed it was just one class, so it sounds like there was a good sized sample and you can make some good inferences from that. Thank you.
Yeah.
Thank you for that question, Adrian, because I was wondering how you were doing that with that particular tool, and I didn't catch that you had blanked the screens for them. So that is very interesting.
This is Olivia. I have kind of a couple quick follow-up questions. So first of all, I really love that you, it was a great presentation, and I really love that you underscored the fact that it's actually monosensory exploration is very unnatural. That's not how we normally do things. My questions are, in answer to Amy's question, you mentioned a bit about some of the next steps that you intend to take. I wonder if you could expand on that anymore. And do you have any other projects or studies that you intend to do? And then second question is, what about the rest of us? What do you see others being able to do with the research that you've done, and what next steps and actions could we take with that? Thank you.
Yeah, thanks for the questions. I will start with the first one. If I got it right, you're asking what are the next experiments we are carrying out. So as I said, there are mainly two that I'm carrying on together with the psychologists. One is an evaluation of the performances of musicians with respect to non-musicians, to understand whether, let's say, training in listening really provides better performances in sonification. The second experiment that we are now running is about training. So we are assessing whether training people leads also to better performances. So we ask people to repeat the same sonification experiment during 5 days in a week. So the first time we explain the experiment, the next days they repeat it. And what we want to see is if with training, the performance is improved and when. So how many days of training do we need? A couple is enough, or do they need to repeat 5 times, or does something change? So these are the two main studies we are carrying out. About what the rest of you can do. I mean, I was presenting the main works I'm involved with, but many of you and many people in the community are working on other experiments and similar ones. I know Adriana, Fia, and I mean, many people are really have interesting studies. So I don't know, maybe getting their perspectives also might be interesting and would open other ways. My main take-home point, I would say, from the experience I had is team up with people that have a different background from you. So I'm an astronomer. I'm teaming up with sound designers and with psychologists. And in this way, I'm really learning how to do things. And I would say that expertise is really fundamental. The other thing is, if you aim at working or doing experiments with blind or low vision people, then team up with them, at least to assess if the experiments are meaningful, are run in a proper way. So I would say team up with people that have the expertise you need. That would be the main suggestion. I don't know if I'm really answering your question, but.
Well, I appreciate, I think you did, and I appreciate Olivia asking that particular question because we're looking at new projects here and how to, as people have young projects, what are the main things, what are the recommendations of people who've been doing this for a while? And it has been our experience with Sonification World Chat, and you have mirrored that as well, that it's important to have a multidisciplinary team and to involve all the user groups that you are target audiences, blind, low vision, children, adults, scientists, get everybody involved in the testing, and the more diverse the team you have, the stronger your project will be. And that is so.
And maybe one more thing, sorry, Kate, if I can add, is what I'm learning is keep your goal in mind very clearly. So if your goal is research, you need a certain type of sonification. If your goal is education or outreach, then maybe you need a different one. I mean, researchers can work with sounds that are a bit unpleasant. The public will not come to your show if the sound is highly unpleasant. For the kids, we decided to use natural mappings instead of the musical instruments that I let you listen to. So the musical instruments are more pleasant to listen to than the water bubbles for a while. But the water bubbles are a lot easier to remember. The association between natural sounds and colors might be easier to remember than the instruments. That's what we have been seeing with this experiment. So I would say keep in mind the goal.
Yeah, did you use any particular methods to figure out the natural sound mapping?
If we use, sorry?
How did you choose bubbles? And, they all make sense, but I'm sure you had choices to make there. How did you go about making those choices?
So we were using literature from the psychoacoustics domain. That's something that people working in psychoacoustics have been exploring for a while. So we use associations like water and blue, fire and red that have been a part of experiments in that domain for a while.
Well, that's absolutely excellent. And with that, we are going to wrap up Anita's session.